Alright, welcome to another JNCIE SP video. Last video I had to cut it short. I'm not sure what was going on. I was kind of feeling weird. I feel really good now. So we're gonna keep going with traffic engineering and we're gonna work on ERO. So last video, as I said, I cut it short, but I was able to do some reading of this for dummies. But I found a number of links that I think are going to be a lot better, so I'd like to read those instead. Now, we did, through that For Dummies link, learn what an ERO is. And actually, we have been playing with EROs this whole time. EROs are a part of RSVP, and they're basically just the static LSP information. So I will show what an ERO is just as soon as I log in here. Okay, so this is a ERO. This is configuration for a ERO right here. So ERO stands for Explicit Route Object. So I think that's a pretty self-explanatory term because you can see I explicitly created the label switch path here. If I were using LDP, I wouldn't have a ERO because it would do that automatically. So let's do a help apropos match help. Match. Okay, so yep, I think Google's going to be the best resource. Unfortunately, the resources I'll have during the exam are limited, but that's kind of the point. They're just testing you on what you know, not what you can look up. But of course, when I'm studying for it, I'm going to have to do a lot of lookups. Okay, so we already did that for dummies. So here's some of the other ones. Looks like we've got a study guide here. That's going to be probably one of the best resources. But it looks like all of these resources are going to be good. Here we have the label switch path attributes in the explicit route object. So let's see if we can get, let's see what the introduction has to say. Yeah, so it looks like this whole thing is going to be about the explicit route object. Yep. So this might be a good one to read. Whether I read it or not, I will include it in my notes. Here we go. So this looks like it's going to be probably the best thing to start with. So far, I think I'm going to start with that. But let's see if there's anything else. Okay, this looks good as well, and it looks like there might be a lab to do. Oops, and I'm actually making a mistake here. I'm putting my notes under the first video I did. I'm going to have to put them under the second one. This will be video number 2. And I believe I did upload the first video. I don't remember exactly, but I can double check that before I upload this one. Okay, so we're good to go as far as the notes are concerned. I might as well just double check that right now since I'm here. Kind of the nightmare scenario is doing something like creating a YouTube channel to help you study and end up spending all your time just on the YouTube channel instead of studying. But so far it's been actually, I think, a really good tool to help me stay productive. So I'm pretty happy with the fact that I'm maintaining this channel so far, and will continue to do it for the unforeseeable future, even after I take an attempt at this exam for my other self-studies. And you can see I already got different topics that I'm going through on this channel. Okay, but yep, I do have the first one uploaded, so let's keep looking for resources for the second one. So here's a whole slide. Perfect. Okay, so just like before, there's going to be a lot of reading in this one, not a lot of hands-on, but there might be some hands-on. I think I'd like to cap it here, so I've got about 40 minutes. So I'd like to just do about 40 minutes of reading, mark that as done, and then move on to the next. Okay, so this is ERO constraints. In this section, you will use explicit route objects, EROs, to constrain the routing of an LSP. EROs function in a manner similar to a source routed packet, in that the presence of EROs in the RSVP path message forces the path message to visit the list of nodes in the sequence in which they are specified. EROs can be either loose or strict. A loose hop allows the IGP to route from the current node to the loosely specified target node any way it wants. A strict hop, on the other hand, does not permit an IGP recursive lookup and will not allow the presence of intervening hops between the current node and the strictly specified target node. When listing a node, you can use either a physical or a loopback address. Note that loopback addresses should not be used in conjunction with strict hops, because by definition a strict hop should be directly connected. Although some Junos software versions allow strict hops that pointed to a neighbor's loopback address, the 5.6R1 version used in this REST bed, or does that say test bed? I guess I can't really see it. I think test bed makes more sense, but you can see how outdated this documentation is, so this really isn't going to be the best resource, but let's continue reading it. Does not support loopback addresses as strict hops for the non-CSPF LSPs. Because the CSPF algorithm generates a complete list of EROs that consists of interface addresses, you can use a strict hop ERO pointing to a neighbor's loopback interface when CSPF is used to compute the LSP's path. To complete this configuration scenario, you must establish an LSP meeting these criteria. Okay, so configuring the ERO constrained LSP. So here we go. This is the command I showed before. Let's read more about that command, and we'll stop here at constrain shortest path first, and we'll move on to the other documents after that. Okay, so the use of primary in this command indicates that a path definition named visit R7R5 exists, and that the primary LSP should be routed according to the EROs in the specified path definition. Okay, so maybe I'm missing a keyword there. I'm missing the word primary in mine. Let's check that quick. Yep, I don't have primary, so maybe I'm not using ERO without the word primary. Once again, CSPF is disabled on the new LSP. This is because the multi-level ISIS topology in the current testbed results in the lack of a domain-wide TET, which in the case of an LSP from R2 to R6 will result in CSPF failures. Note that the restrictions in this configuration task did not explicitly prohibit the use of CSPF, nor do they explicitly state that ERO-based constraints should be used to constrain the LSP's routing. The intent of this wording is to allow the candidate to sync into a mirror of CSPF and TED related analysis, if so they are inclined. After all, a true expert will know when CSPF can and cannot be used. And I know that. It can be used in a single IGP domain. It cannot be used if there are multiple IGP domains unless you get really, really fancy and you're using the same IGP across those two IGP domains. Alright, so here's the next part, disabling CSPF. You now define the visit R7-R5 path, taking care that the ERO specified will not cause the LSP to visit the same link or node twice, because doing so will cause the LSP's routing to fail due to record route object RRO based loop detection. In this example, you opt to use a combination of strict and loose hops that force the LSP to visit R4, then R7, then R5, and then the egress node, R6. There is no need to specify R6 in the ERO because the egress node becomes the last loose hop in the routing of the RSVP path message when the ERO list runs out. R4's loopback address does not exist in ISIS level 1, area 1, so a strict hop pointing at its FE1 interface starts the ERO list. Note that EROs are considered strict by default. The last two hops are specified as loose to accommodate the indirect routing associated with loopback interfaces. Okay, so we've got a specification of loose. This is to accommodate indirect routing associated with loopback. You know what? That might have been my problem before, because I was trying to create an LSP to a loopback interface, and it just wasn't working. And it might be because I didn't have loose enabled here, so it was just getting confused. That's good to know. I wish I could just go and try that, but the thing is, if I do a show MPLS LSP, it's up now. So maybe I can roll back and see if I can get back the configuration I was playing with before. Aha, I can. So let's try, let's see if I roll back 2. Let's see what sort of configuration I get then. Okay, aha, so I've got to include all gold. So yeah, you know what, let's try that. Let's go on the, let's go here, let's commit this. Or, well, before we commit it, let's just make sure that all the configuration is together so that it's easier to revert. Okay, so we're going to have the admin group on there, but we're going to need to modify our to statement to allow it to better process traffic moving between loopback interfaces. And we do that with the keyword loose. So let's look at the, oh, okay, so but that's under path, that's not under label switch path. Now that's interesting. And not only that, it looks like .6 is where this is going to. So I'm not sure what .7 is. Is that the loopback address on this side? I guess I'm not sure what .7 is, and I don't know the subnet mask too. So that adds another layer of confusion to it. I think my main goal here is just to get all the reading done and hopefully understand this better. We've still got one full topic left in RSVP, so hopefully things become more clear as I work through there, and hopefully I'll do more hands-on when I go to the next section, and it can all come back and hopefully make sense at some point. Hopefully before I take the test, that happens at some point. Verifying the ERO constrained LSP. A few moments after the changes are committed at R2, the status of the LSP is displayed. Edit protocols MPLS. Run show MPLS LSP detail. The output confirms that the R2 to R6 LSP is up and that it transits R4, R7, and R5 on its way to R6 as required by the scenario's configuration criteria. The output from the show RSVP session commands provides an interesting contrast in the form of the user provided ERO versus the contents of the record route object RRO as contained in the RSVP path and reservation RESV messages themselves. So let's actually get a little bit of hands-on and let's do a Wireshark Capture, and let's see if we can get those packets just to drive home what is written there, because to be honest, it's all kind of going over my head. I'm just kind of reading it like a news anchor. So let's go in and get some hands-on to really make some more sense of what is actually going on. So I think what I'll do is so first I'll refresh myself as to what we're actually looking for. So we're looking for a RESV message. So let's tear down, or let's just do a clear MPLS LSP, and then see if we get those RESV messages. So we're going to do clear MPLS LSP all, and hopefully, so we're probably going to get some messages that it is torn down, but hopefully eventually we'll get RESV messages as well. And it looks like those are going to be RSP messages, so let's filter out for RSVP. Okay, we've got hello messages. Okay, but I don't see anything about RESV messages. Let's see if it's up yet. Okay, so it's up already, so maybe it would have been component messages dissected. So we've got a terror message. This is what happens when it goes down. So the RESV is going to happen when it comes up. It looks like we got so we got 2 terror messages. Here we go. So we can narrow it down to RESV, see if we get anything. So, nope, we didn't get a RESV message for some reason. I was expecting to get one, but I mean, obviously I don't have a super clear grasp of this yet. So hopefully we can get that by reading some more. Let's see if we have an RRO. I know we have an ERO. Oh, I guess I don't know we have one. I was expecting to have one, but I guess we don't have one. Oh, so that's surprising because we do have a LSP that is up. So maybe it's on the other side. Let's get 2 Wireshark captures going, 1 for each link. Okay, and then let's bounce that LSP again. But before we do that, let's filter out for RSVP, and we'll look at the explicit route data, or explicit route, yep. So, okay, we don't have anything yet, but hopefully if I clear this out, some data will show up. Okay, so it already went back up after being cleared out, so we can see, unfortunately, there is no data. So what about router? Or route object? Or record route object. Yeah, record routes, nothing. Okay, what about RSVP? Or sorry, RESC? RESV. Yep, nothing. So that's really surprising to me. I was expecting there to be something showing up, but clearly I just don't have a good enough understanding. The output confirms that the R1, R6 LSP has been successfully signaled as indicated by the up indication for the LSP state. Further, the display confirms that the LSP's routing complies with the user-provided ERO constraints. The added highlights call out the contents of the user-provided ERO and the contents of the RRO. As a final check, the LSP's forwarding plane is tested by tracing the route to a BGP destination whose next hop resolves to the 10.0.9.6 egress address of the R2, R6 LSP. The 220.220/16 routes coming from C2 should be just the ticket in this case. As expected, the next hop self actions really important because BGP just exchanges information. It doesn't exchange actual routes. So if the route makes no sense, BGP is still gonna exchange it, unlike a IGP such as OSPF or ISIS, where it actually has to be valid routing information in order for it to be sent at all, or received or processed at all. But with BGP, that's not true at all. You're just sending data. That data just so happens to be routing data, so it will be installed whether it makes sense or not. That's a big difference between BGP and other routing protocols. Of R6's iBGP export policy result in a BGP next hop of 10.0.9.6 for the 220.220/16 prefix advertisement within your AS. Because this next hop resolves through the inet.3 routing table on R2, and R2-R6 LSP has automatically been installed as the next hop for 220.220/16 destination, LSP forwarding is now confirmed. The LSP's presence in the forwarding path is clearly indicated by the label-related output associated with hops 1 through 3. With the success of the trace route, all aspects of the ERO constrained LSP scenario have been met. Okay, so that's as far as I think it makes sense to read. So the RFC is going to be the most dense. So let's move to one that might be a little bit easier to understand. This slide here looks good. So the explicit route object puts the engineering in TE. It allows the ingress router. Now remember, the ingress router is the router putting traffic inside of the LSP if you think of the LSP as a tunnel. The egress router is the one that handles traffic leaving the tunnel. So it allows the ingress router to define the path of the LSP through the network. May contain loose hop information. Loose hop defines a node the LSP must pass through at some point. IPv4 shortest path routing used for forwarding path messages. From ingress to first loose hop, between loose hops, from last loose hop to egress router. May contain strict hop information. Strict hop must be the next downstream router, must be directly connected to the local router. Ingress uses routing table to forward the path message towards RTR-D. RTR-D uses routing table to forward message to egress router. Okay. So there's different kinds of EROs. There's loose hop, which uses the routing table to forward the path message. There's strict hop. So ingress consults ERO to locate the first strict hop, forwards path message out interface associated with that hop. Each transit router ensure it is next strict hop in the path. If so, message forwarded to next strict hop. If not, path error message sent back to ingress router. Mixing strict and loose hops. An ERO may contain both strict and loose hops. Loose hops are routed using routing table. Strict hops receive messages when they are directly connected. Manual ERO concerns. Manual use of EROs requires knowledge of the network topology. Loop detection might cause LSP setup to fail. IGP metrics shown below. So we've got E here, and it forwards a path message back to B. Loop detection in RRO by router B prompts creation of path error message. And we saw a path error message. I'm not sure if it was for loops. I mean, I still have it. Oh, actually, no, we didn't see a, let's see, path. Yeah. Or let's see, error. Yeah, LSP error. Nope, what about MPLS error? Nothing. Okay, so automatic EROs. The ingress router can automatically create an ERO for the LSP. Contains all strict hops for the complete path, formed from information contained in the Traffic Engineering Database, TED. TED is populated by information advertised by the interior gateway protocols. Both OSPF and ISIS have been extended to support traffic engineering. OSPF opaque LSA 10, area scope flooding, ISIS TLV 22, extended IS reachability, ISIS TLV 135, extended IP reachability. Okay, so now we're on to IGP extensions. So, we've still got IRO showing up, so let's read this. Both link state IGPs may advertise information which is stored in the TED, interface and neighbor interface addresses, maximum reservable bandwidth per network link, current reservable bandwidth, traffic engineering metric, administrative group information, affinity classes and colors. The Ingress Router uses a modified form of the SPF algorithm within the TED to generate the ERO. Constrain shortest path first. Takes user-defined constraints into account. Okay, so that one is finished. So we've only got 2 left. I've got plenty of time too. I got about 15 minutes. I do have a 1 o'clock meeting, so I gotta wrap it up early, but we will keep reading. I mean, this RFC looks pretty short. Yeah, this is a shorter RFC, so I think I might read that, but let's start. Yeah, let's start by reading this. So as soon as the computations for an individual LSP are completed, the calculated path is written down in a list called ERO, Explicit Route Object. The ERO is a list of all the links that the LSP should traverse. This list is then put into an RSVP path message, and this RSVP path message is used to signal the LSP. Okay, so let's keep an eye out for that RSVP path message. So we're going to filter both Wireshark captures, assuming they're still running. Usually they don't, but we'll just give it a try. And then we'll try restarting it as many things as we can. We'll start by restarting the LSP by clearing it out. Okay, so I don't see a path message. Let's go even further than that, and let's clear the RSVP neighbors. Okay, so hopefully something shows up now. Okay, I still don't see anything, so let's go even further than that. Let's clear the OSPF neighbors. Okay, because we know that RSVP rides on top of the IGP, so definitely be causing some big issues if we clear that. Don't ever do that on, well, if you're not in a lab, be really careful with what you do. You know, obviously don't ever do that. It's not good advice, but just make sure you understand the impact your configurations have, and if your company requires maintenance windows, this is definitely a command that will need to have to go into a maintenance window. There's no doubt about it. All right, so let's see here. Okay, so I think what's going on is it's not capturing anymore. So I'm going to restart these captures, and hopefully we can get it to start. Now I did forget to stop it here first. I think that's a better way to do it, but hopefully it'll work. I can always just restart the client. It's not a big deal. Okay, and then the first command I'll do is clearing off the RSVP neighbors. There we go. And I'll just look on that one side for now. If nothing pops up, we'll look at the other side as well. Okay, so we cleared the RSVP session. Aha, and now we've got RSVP path messages, exactly what we were looking for. I'll stop the capture so that it doesn't get too cluttered, and as we continue to read, we'll be able to go and actually look at what we're reading about. So it's a list of all links that the LSP should traverse. So let's see if we can see what links are in that list. Okay, I think I found it. So here's the links. It's gonna be 3 links. Let's verify by looking at the topology. 1, 2, 3. Perfect. So this is a list of all the links it will traverse. Let's see if we can get things like bandwidth like that. Nope, we don't get that. We just get the hop. We get the subnet mask for the address. Now it does say strict. We can also set that to loose, which would be a good idea if this were on a loopback address instead of a physical interface, because I believe it loose means check the routing table and don't just rely on the MPLS tables, that sort of thing. But I'm not sure if I'm completely understanding that. Let me know in the comments if I'm not. Okay, so yep, so that's all I was looking for, so let's continue reading. Yep, so this list is then put into an RSVP path message, and this RSVP path message is used to signal the LSP. The RSVP path message travels from the ingress LSR downstream to the egress LSR. Every router along the way inspects the ERO inside path message and removes its own IP address from that list. After this, the message is sent further downstream to the router that is next on this list. Okay, so that's interesting. So we'll probably I'm gonna actually start some more captures, and where we had 3 entries in the list on this link here, the first link in the path, I would estimate, I would predict that we would have 2 here and 1 here. So let's see if that prediction is true. Oops. Okay, and of course we're going to need to trigger those messages by restarting the RSVP sessions. Alright, but I will do that right now. It's the next step. Perfect, and hopefully we'll get them all populating with information. I don't see anything yet here, which is surprising. So yeah, it looks like only one of the links had this this RSVP.path associated with it, and this is, I'm guessing, the first link. Oops, so that's interesting. This actually only has one object in it, and this is the subnet on the last link. So it looks like only the last link reported for it. So I'm wondering if it went the other way for some reason. Let's try it again. Let's just open a Wireshark Capture to every single link. Oh, and I'm going to add Wireshark to my notes as well, my tags, because I'm doing quite a lot with it right now. Okay, and we'll run this on every single link. Okay, and then of course we're also going to filter it down for the specific traffic we're looking for. Okay, so all of them started, thankfully. Okay, so it's going to be RSVP.path for all of them. Okay, so now that we've got that, we can restart the LSP by clearing the RSVP sessions. Aha, and we've got traffic showing up here. Let's take a look at the ERO. So here's the ERO right here. It has no keyword object, but explicit route is the same as the, yeah, here it says explicit route object. So we can see we've got 3 links here. So let's see if another one has 2 links. Aha! So here we can see we didn't get any matches. This is over ETH 2. So I think it's, yeah, between R5 and R2. So R5. Oh well, it's not. I'm pretty sure it's going to be this link here. Yeah, this is the only link on ETH 2. And then we know what link this is. So we know we're sniffing this link. It didn't go through this path, so that makes perfect sense that it did not show up in this wire capture. Okay, likewise for this is the other link. But now we've got that desired result that I was going for, where we've got that ERO captured on each link. So I'm going to stop the captures. Okay, and then we'll dive into the packet and see if the list shrinks the closer it gets to its final destination. So here we've got 3. Here we've got 2. And then we already saw the last one, but we'll look at it again anyway. And we've got 1. Perfect. It works exactly as was described. The RSVP path message travels from the Ingress LSR downstream to the Egress LSR. Every router along the way inspects the ERO inside path message and removes their own IP from that list. After this, the message is send further downstream to the router that is next on this list. For an RSVP path message, the Egress LSR is the last stop. The Egress router will send an RSVP RESV message in return to the path message. The path that the RESV message takes is the same as the path message, only in reverse. The RESV message is used to reserve the resources for the LSP. Every router will use the RESV message to tell the upstream router what label to install into their LIB. Label information base probably. After an LSP is signaled, there are 2 easy ways to find out what the content of the ERO is. You can issue a show MPLS LSP name XX extensive and look for the computed ERO. Additionally, you can issue a show RSVP session name XX extensive and look for the EXPLCT route information. Oh, you know what? It probably is going to show up as this because it's going to be abbreviated. Let's try these 2 commands and we're going to look at the content of the EROs. So if we do it on the first router, the content of the EROs is going to contain 3 entries, 1 for each of the links that it has yet to traverse. If we were to look at the next router, we're only going to have 2 because it already traversed the first part in the list that was included in the ERO on the first router. So the first, I don't know if it's the first thing, but one of the things that happens when a router receives an ERO is it removes the link that the ERO was received on. So as it goes, it decrements it. We saw that very clearly. But let's see how we can look at exactly what we looked at in Wireshark, but on the device itself. So it would be show MPLS LSP name, and then it's going to be PE2, I think was the name. I don't know. Let's do a show configuration. Pipe, oops. Protocols MPLS, pipe display set relative. Okay, and now yep, so it's 2, but it's R5 instead of PE2. So it's going to be show MPLS LSP name to R5 extensive. Okay, so now we've got, so here's the list. It's got 3 entries. This is everything we saw in Wireshark. Let's see what the other command has to say. Oops, so we've got to have a name of the RSVP session. I'm not sure what the name is going to be, so let's just use the same name for the MPLS LSP, and hopefully that is the name of the RSVP session. It looks like it is. So we're going to look for, yep, and it's missing an I, just so this is how it appears. And there we go, we've got the path. So let's do one of these, maybe not both of them, on the other 2, and hopefully we'll have the same results. Now I have a feeling that because the ERO is not actually configured on these routers, it's only configured on the Ingress router, and then it's used to send ERO objects. But the actual ERO itself, if I do a show configuration protocols, MPLS, pipe display set, pipe no more, you can see very clearly there's no ERO configured here. So let's see what happens if I do this. So it looks like I do have a LSP. So let's do name to R5 extensive. Okay, perfect. So we can see it, and then we've got the, yep, so now we've only got 2 links. Perfect. So even though it's not configured on here, we do have an ERO on here. It's just populated automatically because this is a transit router within the label switch path. And we can see that the link that it already traversed has been removed from the explicit route object, which is just a link, just a list of links it has yet to traverse. Okay, so let's run it on router 4. And now there's only going to be 1 link. Oh, so it's going to be show MPLS LSP name to R5. It's going to be extensive. Okay, yep, and we've only got 1 link in there. Perfect. Now we do have the record route. This does have 3 links, or actually no, it looks like it actually has 4, so it includes the very last one as well. Let's take a look at the record route for the first one, just because I'm curious about that, and it was in the reading. So I just want to refresh myself quick on that. Okay, so it looks like there's only 3 in there. Let's see what the other command has to say. That's the RSVP one. There we go. So yep, the record route is going to include an entry for itself, unlike the explicit route, but it will just say self instead of like the IP address for itself. So yep, record route's pretty easy. It's just a record of everything, and then the explicit route is just what's happening now. So in addition to seeing what's happening now, you're not put in that situation where, oh no, what link did it come from? Because you can look at the record route and you can say, okay, so what happened before? We can see what it's going to do, and that's recorded here. But what did it do before? Oh, it's in the record route, and we can see it didn't do anything before. It actually came from here. So let's do that for this as well. Okay, so now we can see it's got one more link left to traverse. So where it is now, because it hasn't traversed that last link now, so it's not here, it's before here. It's got this left to do. So this is where it is. It's on itself. But what it has to do next is in the explicit route list. What it needs to do in total is in record route, and it looks like this records where it came from. So you can see the .2s changed to .1s. Yeah, so these were .2s because it's got to be sent to .2, but keeping track of what actually happened, the .1s were used, not the .2s. So that's what's in the record. So yeah, I think I understand it pretty well. I'm pretty happy with what I've read so far. So let's read the default. Yeah. Oh, it looks like there's a lot of extra to read. Let's see if we can get through these in like 1 minute. So change the ERO by changing the metric. A quick and easy way to force the LSP to take another route would be by changing the metric of this link. When we choose to do so, we can alter the cost for the link in all IGP related calculations, or we can change the cost of this link for RSVP TE purposes only. Let's change the link cost in ISIS for RSVP TE purposes only like this. So TE metric, perfect. I don't have ISIS set up though, I have OSPF. After committing this change, we will force the router to signal the LSP again. We can do this by clearing the LSP. After the LSP is cleared through the clear MPLS LSP command, it is automatically set up again using the new metrics. To verify that the computed ERO now differs from our previous output, we issue the same command again. By altering the TE-metric, we only alter the cost of the link for calculations done by the CSPF algorithm. We can verify this by looking at the information in the TED. We can look at the information stored in the TED by issuing the following command. The metric that is listed first is the TE metric. This metric was used for the CSPF calculations. The IGP metric used to calculate the routes in the inet.0 table remains unaltered. Both OSPF and ISIS allow us to do this. So I'm not sure how you do it in OSPF. I can look at that in the next video. As an alternative to the show TED database extensive command, we could have also used the show ISIS database with the extensive option to verify the same thing. Show OSPF database opaque area extensive when running OSPF. So that's going to be the end of this topic. I really think I did it justice. I learned quite a bit. So I'm going to mark it complete. Okay, and now the really good news is I've got a whole topic here complete, and oops, so I will mark that complete as well. Okay, and then I'll see you in the next video where we go through high availability techniques for MPLS. Thanks for watching.